Alright, welcome to another. See, disrupted again. It's always the stupid icon. It doesn't change. The icon doesn't change when it's recording. It's supposed to change. And there I can tell that it actually is recording versus not recording. Oh, just so much. These little aggravations in life, the little ones, they just stack up and stack up and stack up until you got a whole pile of aggravations. Like miseries. My back is a little gimpy today. Anyway. So, yes, draft physics video presentation. Physics girl. Ugh. So, I like women. I like women that are smart and do smart things and, show that they can, play a good game. And the game wouldn't be some sissy girl game. No, the game would be the game. The game. The doesn't have to be a man, doesn't have to be a woman. It's just a game, and you're playing it. And I just hate that, when women dumb down their game and overtly do it as women. Silly and trivial and goofy and fun. Yeah. Pathetic. So go to college to be a silly person. Fine, whatever. Don't think so. Anyway, so this is on the fundamentals. She's doing these educational videos, quote unquote, where, they don't even have Newtonian physics right. In the sense that, again, Newton didn't speculate on causes. He just documented effects. So you can't really say the Newton perspective because there really isn't a perspective. He's just saying, yeah, the star has light, okay, and it gets here. And that's it. I mean, it's just a quantization of what is, and then there was some, obviously the orbits and stuff. He did it's not what it looks like. The sunrise and that kind of stuff is kind of it'll fool you if you don't think about it. But again, it's just effects. It's not really causal information. And they're still, they still haven't answered the fundamental questions. I mean, they're still just doing effects and pretending they're describing a cause somewhere. And they don't come anywhere close. And so they're teaching, and they don't teach with any kind of, well, this is what we've come up so far, and this is sort of our evidence. And let's hear counter arguments. Let's, debate whether or not this is a rational way to perceive things and to understand things. Because maybe there's some obvious facts, and they are obvious. We don't have electron guns. We don't physically, we don't have some mechanism to shoot electrons wherever we want to in space. We can't just send a message in electrons, a beam of electrons to outer space and tell them who we are and what we are. Can't do it. And they should be able to explain. Well, that seems kind of strange, right? It's matter. I can throw a wrench and it'll get to Mars. Well, how come an electron can't get there? And they don't ask that question. And well, I've sort of jumped the shark here in the sense I've jumped the let's watch them do it wrong.
Today's lesson is Newton's laws of motion. And today's theme, may the force be with you. It's a little clumsy. May the force be with you.
So who is this made for? What, 7-year-olds? Who are you doing these with? Why don't you just say, I'm doing the Barney the Dinosaur physics. And this is what to be interested, I have to be wacky and silly because, we have to turn all minds into silly feeders. We have to get them addicted to meat eating and addicted to silly shit. These are all important things to do to children, is to make them think that life is just some silly game, that nothing's really at stake, nothing important happens here, you can't blah 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 blah. When, of course, everything you do could kill somebody, and they don't tell kids that. So if I'm going to do an instructional video to children, I'm going to tell you everything you can do can kill somebody, every fucking thing. So measure what you're doing, because it might hurt something. Think about it. Think a lot, and then do nothing. That's the safest bet. Just listen and learn, okay? And then when you're smart enough, you'll know, fuck, my parents were assholes. Because they made a human being that doesn't have any decent game to play except this silly bullshit.
Oh, wow. As someone born on Star Wars Day, May the 4th, that saying never gets old. So,
this saying never gets old. Well, yeah, it does sort of, incredibly old.
Force.
That never gets old. Raspberries. Raspberries never gets old. Yeah, it still works.
Pulling. What makes things accelerate?
Yeah, yes, and you're not going to give us any information at all about what makes any of that happen. And the rest of it is just explaining what we can all observe. But you're not going to explain anything to do with anything about a cause.
How much do they accelerate? There's this relationship between...
I have the volume all the way up, so this really should be louder than this, and so I have no explanation for that. I mean, I could pause and fix it, but fuck it. It's not that important anyway. She's just saying silly things.
Force, mass, and acceleration.
So, right, force, matter, and interaction that causes acceleration. That would be the way to look at it. A force acts on matter. Matter moves, okay? But to move, you have to change it. It takes time. You can't just bang, I made it move. Now, some hard things, you can literally do that, and they'll accelerate fairly rapidly. They'll get the idea that they have to go somewhere. But smushy things like us, well, we don't get the idea right away, and so we'll kind of push into the chair, and we'll kind of change our shape, and our face will get funny. And shit'll happen to us because you can't accelerate all our pieces evenly. That should have been in here somewhere.
We're going to understand that relationship.
No, you're not going to understand any of it. They're not going to explain a single reason why an electron ever decides to move, or a proton ever decides to move, and in turn an atom ever decides to move. And they're never going to really say the truth, which is the only universe that exists is the small universe. Everything else that happens because the small universe did it first. Okay, it's in control. Nothing else is. The small universe makes all the black holes and all the other crap you want to imagine out there. Yes, the small universe made it first.
Quantitatively with math. So that...
Yeah, so we're going to understand it quantitatively with math. La 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 la. You're not going to understand anything. You're really not.
Our lesson today. So let's get started with Newton's first law, inertia. Let's think back about that skater. This trick is really fun for physicists to see because it's unexpected. You kind of want the skater to accelerate with the truck, but he doesn't.
So yes, it's not unexpected for anybody has the tiniest physics education. Not unexpected at all. It's completely expected. See, somehow there's absolutely no reason for my volume settings to be reduced. So I do a reboot and the volume settings are fucked up. I hope this is recording the video.
Confusing demo of this same idea. I have a regular balloon hanging from the ceiling and a helium...
Didn't work either. Okay, so I thought that would fix it, but it didn't. So this balloon thing, that's about the density of the air and blah blah blah. So he accelerates forward, the blue balloon goes backwards, and the helium balloon tries to stay where it is because of its buoyancy.
Balloon taped to the ground. I'm in a Porsche, which can accelerate really quickly. So which direction do you think the balloons will go? And hit it! The balloons went separate directions. I mean, initially they stayed right where they were, but then they went separate ways. So before...
Well, it just has to do with the air in the car. So if you take the air out, you get a different result.
Show how these two weird demonstrations are related and how they're explained by Newton's first law, we actually have to think about why things move. And when you think...
So again, she's not going to do that. So again, they keep saying they're going to talk about something they never talk about, which is why. They don't answer the why question. They just answer the what question. What happens?
About motion, you'll quickly come across the name Isaac Newton. Back in his day, in 1600s England, they didn't have cars or trains.
Oh, yes, but they had plenty of moving things. They probably had something close enough to a, snowball. Lots of things were invented long before Newton, so they could understand snowballs and rolling down hills and all kinds of stuff and rocks falling down and blah, 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 blah.
So the fastest thing you're going to see around town is probably a cart pulled by a horse. If you ask someone at the time what makes the cart move, they would probably say it's the horse.
Yes, of course, of course. It's the horse, of course. Of course it's the fucking horse. What, do you think something else is making the movement but the horse? Why would she even go there? And why would it have blinders on in Newton's day? Horses didn't need blinders in Newton's day. They didn't need to be shielded from car traffic. Fuck.
You take away the horse, the cart stops moving. Like, what's wrong with you? Why would you even ask this? It's obvious. It seems obvious.
No, it is obvious, and it is the complete answer. Without the horse, the cart doesn't move. It's just a fact.
Moving things will stop unless you keep pushing or pulling them.
Right, now that's the trick. Now, do you really understand that concept completely, in the sense that you have complete assurance through all experimental evidence demonstrates that all things, once propelled through space, will keep moving? No, you don't.
But is that right? We can do something that those people in the past couldn't do. We can go to space. I mean,
yes, but they could create vacuums, and they could play around with vacuums, and so they could have understood a feather and a thing falling at the same rate and blah, blah, blah. So to some extent they were catching up.
Not us, but like some people can go to space. If I'm in outer space and I throw...
Yes, I wish that we could send you to space. I just wish we could buy you that ticket.
Olive the otter, she just goes. She moves and keeps on moving. Space does not have air resistance.
Right. But it still does have air resistance, in the sense there still is a hydrogen and gases in space, so there still is some resistance. And it's a real fact because, if we send something into space going very, very fast, those things are going to be real problems. You hit a hydrogen atom and it's going to blow a hole in your spaceship and lots of things like that. But, oh yes, for the sake of the argument, okay, if you want to talk about a perfect vacuum, fine. And things will keep going, again, fine. But where does that stop? And where it stops is where we already know. Is that the only thing that comes from outer space in the terms of radiation, we don't get protons hitting us and we don't get electrons hitting us. We get nucleuses, helium nucleuses. So the smallest thing that comes to us as radiation, and those nucleuses end up hitting the ionosphere and end up breaking into pieces, and then we get electrons and protons. But there are no... out in space, there's nothing but helium nucleuses to deal with, and light. So all you have is gamma and, I always get it wrong, alpha?
Anything providing friction. So unless she smashes into the moon or another planet, nothing will stop the otter and she'll keep moving forever.
Right, so again, we know this isn't true. So we built these really expensive accelerators and all that stuff, and has any of those accelerators ever actually been able to capture anything and perpetually keep it going in a circle? See, I mean, the trick is we are supplying the bending. So you create an accelerator, a round thing, and you send some crap at a high velocity in the accelerator, and you have a bunch of magnets, okay, around the whole damn thing to keep pushing. All right, to force it to curve. So you're applying the force just like the gravity is applying the force to the planet Earth and forcing it to orbit. Well, we're doing the same thing to protons and electrons and whatever, ions of different kind, PEI. Used to vacation there. So this stuff keeps going around and around. But how come we can't keep it going around and around? How come we can't just feed in a bunch of crap, just keep it going around and come back tomorrow and it's still going around and around and around? And how come? Oh, that's right, because all of these things have to keep being pushed, and as soon as you stop pushing them, they stop moving. So it's not like a wrench in space somehow. For electrons and protons, I can take that, go up in the space shuttle into space, and I can shoot electrons at the moon, and I can shoot protons at the moon, and they won't get there. So all of a sudden this breaks down. This isn't true. All matter doesn't behave that way. But they don't care. That detail has... Look, am I the only person that's revealed the big hidden secret? No. They all know about it. Those people in accelerators know they have to keep pushing this stuff. They know when they trap it with, to measure the mass of an electron. This is an experiment they did back in the 50s. They can't keep the beam in there. Somehow it doesn't work, even though they're providing the bending force. So the stuff doesn't have to lose any momentum at all because you're providing the force to bend it. So it's not using any of its own velocity to curve its path. So the trap should be perfect. You have a vacuum, you have a magnetic trap providing the bending. So where does it fall apart? Why doesn't it work? They never thought about it. They're physicists. They're not supposed to think about that kind of stuff.
You can see something more easily that people in the 17th century could not see.
Yeah, you're not seeing anything, okay? You're just making stuff up, and you're assuming, and you're jumping the evidence, and you're contriving a theory out of the scantest it looks a little bit like. You're just a bunch of people looking for Sasquatch, and you'll take any kind of image. You don't care if you can see the zipper on the guy's ape suit, so what? You are believers. You're religion.
It's not that things in motion need forces to keep them in motion.
Yes, they actually do. And that's the whole cause of gravity. Surprisingly, yes, that explains what gravity actually is. So you would have been able to figure out what gravity actually is if you actually didn't fall for this. You keep reading out of your stupid Bibles instead of looking at your Darwin. You won't read Darwin, but you'll just glorify. Oh, sorry, I didn't realize when I was drawing that you weren't seeing much of it. That's enough of it. You don't need to see me. So look, so the simple argument is that electrons and protons never move unless they're pushed by a force. That is, and a force can be a bunch of force that piles up, like a gamma ray is pushing it, or an X-ray. So an X-ray is basically pushing the electron, or what you might call a muon, or some other kind of idiotic thing. But anyway, and the truth is that it impacts other force as it's going into it, and it hits more of this little force stuff. And each time it does that, it reflects a piece of this, and a piece of this, and a piece of it. Keeps reflecting that off, and it's reflecting this way. Little bits bounce off, and the end result is that a force that was going the speed of light is going to spend some period of its life pushing matter, and it's going to push matter much slower than that. Okay, half the speed. So you could say this is 5% the speed of light for each little bit, and the more you stack up, the faster you can push something. But the limit still is the speed of light by some sort of curve, that it gets the less effect on acceleration, the faster you're going, the harder it is to push, kind of idea. But anyway, so the basic idea is that you're taking a force that would have been here and in the universe, and now it's only here. You've taken away some of its momentum by reducing how fast it travels a distance. The force can't travel the distance the same speed because it's pushing a piece of matter. Therefore, it's lost a little bit of momentum. Therefore, an object that has these things in it that are moving is going to take in more energy. Is going to go in. Speed of light energy goes in, and it comes out a little bit later. Okay, it comes out slower, and so that means it's lost a little bit of its momentum, and that's gravity. If you're in this difference between the external universe and what's coming out of the object, then you're going to be pushed into the object because what's coming out is a little less than what went in. And that explains where gravity comes from. Every time an electron or proton moves, it moves because it was pushed by a piece of force for that period of time it's moving, and that means the force was reduced in speed, and that means there's a deficit in force. There, now gravity's actually explained. It's actually pointed out where it comes from, why it exists. Why does the electron move? Because a force is pushing it. Fact. And it's using energy to do it. Fact. And that's gravity.
It's the opposite. On Earth, there's always wind or air resistance or friction in wheels or sliding friction or something.
Right, and there's also always this force stuff too that's made out of gravity. That's what gravity is, force bits. So yes, it's always in the way, dragging. There's drag all over the place. The whole system is dragged to a halt. until you put a helium nucleus together. And then you can overcome drag, because then you're compressing the nuclei, and by compressing it you create more energy. Just as if I had ping pong paddles with a ping pong ball bouncing back and forth, there would be more interactions, same amount of force, one piece of force, but there's more interactions the closer I make the two things, therefore more energy. And that's how you can overcome drag.
Some force that's acting to slow things down. The forces act to change the motion. Absent those forces, things do keep moving.
So she asserted it again when no, they don't. Just fact.
Or they never move. There's this really fun party trick where you hit the top of the
party tricks. You know, it's all it's about is tricks and gimmicks. La 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 la.
Glass bottle with water in it, and if you hit it hard enough, the bottom of the bottle sometimes breaks out. And the reason why is that thing we just talked about. As you hit the bottle, it moves fast with the hammer, but the water stays behind and creates this area of low pressure at the bottom, and the pressure is so low that the water turns to a gas and creates vapor bubbles that quickly collapse with such a violent shockwave it breaks out the bottom of the glass. All because...
Well, you create a high vacuum is what you're doing, really. The water moves slower, the glass moves. There's a vacuum created between the two. The vacuum obviously condenses all the water vapor, and it's a vacuum, and it's just too much vacuum for the bottle to withstand, so it breaks.
The water wanted to resist motion. So that's the first and the simplest of the three.
So again, nothing wants to resist motion. So again, this is so stupid a thing to say. Don't. The problem is that it takes time. Motion takes time for substances. Different substances have different time. All right, and a bottle is a perfect illustration in a sense. The bottle tells you the answer, okay? The water is a bunch of molecules loosely held together. The jar is a bunch of molecules tightly held together, all right? So, you know, the obvious truth is you move the bottle, the water takes time because the atoms are loosely held, which means the atoms are far apart or they're not as connected, you know, blah, blah, blah. And so when you're applying your acceleration, you have to get to all of the atoms. All of the atoms have to be moved. And it takes time to move them when they're not rigidly connected. So unless I have them rigidly connected, they're all sharing hard electrons, they're all in hard positions, and I push one electron and it moves through the others really quickly. Like in a metal, it's very quick. But in mushy substances, it's not quick. And so to accelerate all the atoms takes time because they all have to interact with each other and bang into each other, get closer to each other, do all this stuff. So it's just a time equation. So it's just about the density. In a sense, you could say density was the argument, you know, how dense the material is. But, you know, it's about its rigidity. It's about how tight, you know, how much, you know, so you can apply force to one electron and it's communicated to everything else really quickly. You know, speed of light, in a very straight line kind of ways, versus all of this chaos, versus having to, you know, push this and this and this, and they're all moving in different directions. The water has molecules moving in different directions, so obviously you have to change their direction entirely. So it's just about time. It's about how much time does it take to change the direction of every single electron and proton. I mean, that's what you're doing. When you're moving something, you got to move all of it. All of it's moving. All of the atoms in my hand have to be compelled to go from here to over here. And although it looks like it's happening really fast, you know, our world is moving so frickin' slow compared to the tiny verse, right? I mean, that this is days, you know, in terms of, you know, atomic interactions. This is a really slow movement, even though it looks to you really fast. It's just because you're running really slow. And so it does actually take time for it to happen. But that's all it is. Every kind of substance accelerates differently, and it's not because it's resisting acceleration, it's because it takes time for the force to hit all the little bits and get them all moving in the right direction.
Ideas that we're going to explore today. The idea that things keep moving until something stops them. The flip side of this idea.
Okay, so, and again, the thing that's going to stop them is drag. That's a real thing, and it stops electrons and protons all the time. And, you know, but you can arrange the atoms in such a way to overcome that drag.
is that things that are stopped will stay stopped until something moves them.
That's the truth. The truth is if they're not moving, then you're going to have to change that. You're going to have to change a force somewhere. The forces are equal if they're not moving. Doesn't mean they're not moving. It just means that the forces are all equal. The same ones that are affecting you are affecting it. And you have to change something to change which way it's going to go. You have to apply a force. You don't, and that should be telling you something. That, yeah, it does need a force to go somewhere.
This property applies to
I'm goofy and silly.
anything that has mass. And the property is called inertia. It's inertia, not inertia.
Even the word is just stupid. There's no inertia. It doesn't mean anything. It just means, okay, we can understand that everything has a state. You're halfway between the Earth and the Moon. Well, 3/4 of the way, whatever the point is where the gravity pull from each one is equal. Well, you're still in a lot of gravity. You're still being affected by gravities. It's just that the two effects cancel out. You're being pulled one way as much as you're pushed the other way. And again, there is no pull. There's just an absence of push. Hey.
Newton was the one who really refined this idea of inertia. And this idea was one of several ideas so important to our understanding of the natural.
Again, it's really not nearly as important as understanding the small universe is the only universe. That's really important. Understanding that there's force and matter doesn't do anything until it's forced to. So they're properly named in that sense. Force has to force something to move.
World that we've come to call them laws. In fact, the concept of inertia is Newton's first law. Newton came up with 3 well-known laws and wrote them down in his...
So you don't need any inertia to just get the point that things don't do anything until you act on them. They don't start and they don't stop. They don't do either one of these things until they're acted on. But the point is Newton didn't know, is everything's being acted on an insane amount per second. Per second, the universe is producing, gazillions of little pieces of momentum are hitting you every second.
Which I actually got to hold during a visit to London.
Oh, see, it's so exciting to be a celebrity because you get to do all these little privileged little things because you're a little privileged person. La 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 la, because you do little fucking girly physics. Shit.
Which was probably the proudest moment of my physicist life. It was the original manuscript from the 1600s. Anyways. Inertia is
anyways, someday maybe you could be a celebrity too and get to hold an old book too. And maybe you get to lick it. Yeah. I asked to lick it, but they said you have to pay a whole bunch of extra money to lick it. So I didn't want to pay that. Because I have to, make more ad revenue. Oh, God, I hate this planet. I just can't stand it here. Fuck.
First of the 3 laws, and you might hear it stated as something like an object at rest remains at rest and an object in motion remains in motion unless acted upon by a force.
There you go. You don't need the word inertia. Yeah, you just need the idea that everything's in a condition and its condition will stay that way until you change the condition. So it's 79 degrees and blah, blah, blah. And unless another sun shows up or something blocks the sun, cloud, something has to happen to change the circumstance for the circumstance to change. Wow. I'm not saying we shouldn't say good. Newton wrote that down. But frankly, yeah, that's one of those ones where you go, duh, I already figured that part out. Things have to change before they change. Yeah, I got it.
Basically, Newton's first law is that inertia exists. So then, what's going on with that skater in the truck? Look carefully.
Oh, like this, and again, this is so trivial. You're just saying, who are you doing this physics for? What level of retard are you doing it for? Duh, 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 duh. I mean, 3rd graders? Then you should be teaching this even sillier.
As the truck accelerates, the skater basically stays still. There's so little friction in the wheels of the skateboard that there's very little force acting on the skater. So the truck accelerates right out from underneath while he just sits.
Yeah, the more interesting demonstration was actually having a truck go 60 miles an hour and shoot a basketball out of a cannon. Okay, in the opposite direction, have the basketballs drop straight down. That's what those whatever guys did. That was interesting. All right. Because then you're really You're doing something that took real precision, to have just enough, cannon push to compensate for just going exactly the right speed and all. I mean, to get that right, good trick. Rolling off the back of the truck, not much of a trick.
There, inertiating. And as for the balloons, well, this one's a little trickier because the thing that stays behind, resisting motion, is actually the air inside the car. It stays behind and ends up getting compressed toward the back of the car, which creates a high pressure, and that high pressure is enough to...
Yeah, so it's just about the air pressure in the car, so it really has nothing to do with the subject at all. It just has to do with the buoyancy of helium. So yes, it really is kind of not a very good example when you're trying to do the laws of motion. To add something complex like the buoyancy of atoms, and the fact that the helium atoms are less dense and therefore they float. And when you put a whole bunch of thick water behind them, that they'll have to float ahead, even though it's going against the laws of motion in a sense.
Push the very not dense helium balloon forward, just like helium balloons will rise into the air where the pressure is lower. Okay, great. That's Newton's first law. Maybe I should start writing these down.
Oh, so we're really going to get silly. Thank you. I just love when you get extra silly. Extra silly is just so much more fun. There's nothing, it's just, oh man, you people really, you're hurting me. You're hurting me. Gotta quit voting for this kind of crap. You can't keep voting for this. This becomes president. You fucking insane lunatics. The whole world's turning into a fucking cartoon and all the intellectuals are just applauding.
Woo-hoo! All right, Newton's first law, inertia exists. But what can force something to change its motion? Well, muscles, cars with engines...
So they waste all this money on this stupid garbage props to write down a sentence. Yeah. And it always helps. When you say things overtly, fuckhead. Now, if I don't write that down, you really don't get it, right? I mean, you never heard it. Your brain doesn't know what to do with the word fuck and head unless you see fuckhead actually written. So unless you write the word inertia, you'll have no clue what I'm talking about. I just hate when physics does that. The college professors will sit there and waste time writing whole paragraphs on the board that they just said. They just said the shit. What are they writing it down for? I heard you. I don't need you to write it down. You're wasting goddamn fucking time. I'm paying you whatever, way too much money per second to sit and listen to your fucking lecture, and you're wasting my time writing paragraphs that you just spoke? Fuck.
Gravity that can pull, all these things exert pushes or pulls to accelerate us. And we call these pushes or pulls forces.
There we go. You got one right. Yay! All right. Yes. There you go. And the force actually has to be a something. It's carrying momentum. It actually has to be pushing something. That's all it can do is push, right? There's no fucking pull mechanism, right? So we all know that you're either pushing or you're not pushing. But there's no pulling. There's just pushing and not pushing. Somebody could be on one side of me and push me. Somebody could be on the other side of me and they're not pushing me. So therefore, I go towards the not pushing.
Forces are what force us to change our motion. Who would have thought? When I change your velocity, I accelerate you. Here's a subtle but important...
There, yes, and we already went over that. And depending on what you're made out of, you're not going to accelerate necessarily consistently. Everything will accelerate at a way different rate. It'll take a long time to accelerate a piece of Jell-O by poking it with my finger. The whole Jell-O will take a while to get going.
Distinction. In a lot of situations, accelerating means speeding you up or slowing you down, but it could also mean changing the direction.
Yeah, that's all it is. That's right. All you're doing is applying change. Change. That's all. Change. You've changed what's happening. You're now poking it with some kind of force from some place. And that force will have an impact on what it's doing because now it has to be added to the existing circumstance. The existing circumstance is... Now you're going to either take something away from the existing circumstance or add something to it, and that's all there is to it.
your velocity. Say you're turning left in a car. The road pushes the wheels sideways, but you stay going 30 meters per second. That change in the direction of your velocity counts as an acceleration. That's an idea we're going to explore more in a later lesson.
Yeah, wait, no. If you turn the wheels, you're going to create more friction and you're going to lose velocity. But whatever. I don't want to have to explain that basic fact to you.
To circular motion in orbit. Okay, so you push something like a cow. We'll make it a square cow for simplicity. I actually have a square cow. Look how cute it is.
Oh, it's just everything's got to be a cartoon. Look at that. Isn't that cute?
How much will the cow speed up? Well, it depends on how hard I push it, right? The force. Duh. But it's also going to
No, it's going to depend on whether you're pushing it with bullets or a cattle prod in its butt. It depends on how you're going to force all the atoms in the cow to move. Are you going to force all the atoms by pushing one hair? Are you going to try to push all the hairs? Or how are you going to get all the atoms in the cow to move? And that's why the cow has a spinal cord and a whole bunch of other things, because cows sometimes need to get the whole thing moving, and so it's all tied to something rigid. So then you can push on the rigid thing and the whole thing will move.
Depend on the mass. That makes sense, right? The more massive an object is, the harder I have to push it to get it to accelerate.
Right, and again, it's not just about mass, it's about how you apply the acceleration. So again, we're back to this Einstein thing. Gravity accelerates your atomic structure. It accelerates your nuclear parts. Your electrons and protons are accelerated. All right, so it's right at your core. It's getting at the core of what you're made out of. The little raindrops are hitting that. All right, and all the other accelerants you use have to push on actual atoms and locations, and they cause a whole bunch of deformation in one place, but not much throughout the whole thing. So you end up accelerating pieces of you really fast and other parts of you not at all. So if I accelerate you by shooting bullets at you, it'll be a very different than I take the same exact amount of energy and I push you with a giant piece of paper or something, going exactly the same, having exactly the same momentum, mass, and velocity as the bullet. The more surface area I can spread the movement over, the more quickly I can accelerate all of your cells without having places where I accelerate way too much and places where I accelerate way too little.
And this all brings us to Newton's second law. An object's mass is the ratio between the force you apply to an object and the acceleration the object will.
Well, so again, that's just bullshit in the sense that its mass is just a standard for how well it absorbs force. So it's just about how well it absorbs force in the sense of how much can it absorb a force. But again, how it absorbs a force, the mass doesn't mean anything if it's jello versus steel. The two will be accelerated differently if you have to apply the force externally and you're not using something standard like gravity. I mean, gravity gets right to the atoms, so then it's just about the atoms. But every other force you come up with just about is not going to be like gravity. It's going to affect atoms at a time, a laser beam even. It's going to create deformations in the substance. It's going to accelerate pieces of you very fast and other pieces of you not at all.
Experience. And this is directly related to our first idea of inertia. Mass, whether it's the mass of a person, a skater, a cow, it's the measure of the inertia of an object.
No, it's just the measure of the number of electrons and protons that have to be moved, period. That's all it is. All right, period. You have a certain number of them. They have to be moved. They're going to absorb a certain amount of force in that process. So if you thought about the matter bits being a sail and you're catching wind with them, or it doesn't matter. It's how much can it catch? How much of the force can it catch? And how much of the force it can catch is completely dependent on how many electrons and protons there are. That's the way to understand mass.
Object. It tells you how hard you need to push it in order to accelerate it. Bring the A up, and boom, F equals ma. That is Newton's second law. This is probably the most fundamental and important idea in all of physics. This is the big mama.
Oh, this is scary. Obviously, the force it takes to accelerate something again depends on how efficiently you're applying it. So that formula only works in perfect circumstances. It doesn't have anything to do with the real world, where you lose all kinds of your force through heat, and you're not going to get the same amount of acceleration. So that formula ends up being derived into a bunch of catches, depending on what you're moving. So it's kind of, it's this universal formula, but it really doesn't mean anything, because it can't be applied in any way to the non-standard reality. Masses don't come in the same atomic form, therefore they can't be moved the same way.
Equals ma is to physics as the force is to Jedi. Given a force and a mass, I can tell you the acceleration that you'll experience. Measure the force on an object and the acceleration it undergoes, and I can tell you its mass. Start with F equals ma.
So it's just not true. It really depends. Like I said, if I'm applying the force in the form of a bullet, you're not going to move very much. Okay? I mean, parts of your brain will move and they'll fly out and hit the wall somewhere, but the rest of you isn't going anywhere.
Add 400 years of people doing physics, and I can send a rocket to Mars.
Atlas V with Curiosity seeking clues to the planetary puzzle about life on Mars.
Oh, yeah, so just that was even depressing. Right. That, okay, we're going to have 400 million coincidences happen on Mars, and there's going to be life on Mars. Okay, there's going to be the creation of a DNA molecule, and it only can be one DNA molecule because all the rest of the DNA molecules failed. So one version of DNA is the only one that works. Change one little amino acid and it all of a sudden doesn't evolve, doesn't turn into anything, doesn't work. Right? I mean, there's so many examples of how rare the process is. How preposterously unlikely. Only one neuron. That's it. So all thinking only happens because of one electrical cell that was created somewhere in the past. One event. And it never happened another way. It only happened that one time, that one way, and never, ever, ever any other way. But let's not pay any attention to the facts. No, let's assume there's life on Mars. Because there's water, and that's all you need. A glass of water, and poof. The elephants will just fly out.
Wow. But almost as important as F equals ma is the units of force. So the unit of mass is kilograms. The unit of acceleration is meters per second squared. So the unit force is kilograms times meters per second squared.
Again, these are only ideals, so it doesn't have anything to do with the real world, where if you want to move something, it depends on what kind of condition it's in. If it's jello, it's going to deform and do all kinds of things that are going to get in the way of perfect acceleration. And so unless I put it in a cart or something to contain it, a container, I'm going to have a hard time accelerating it. A really hard time accelerating it. Especially like in space. I can just sit there poking. You just see, why the fuck aren't you moving? I'm poking you. I'm applying a force. Why aren't you fucking moving? Am I supposed to say Newton was wrong? No. It's just not applicable. Newton's F equals ma is a force law that only has to do with when you're using gravity as the force. Some sort of force that is moving the speed of light. Not when the force is contained in a bunch of atomic and charge features of atoms, and I push one set of atoms against another set of atoms. That doesn't work.
A mouthful, so we give it a name. The units of force are called newtons, as in Isaac Newton.
Right, and nobody uses this gibberish. This isn't, so she's teaching like third graders or whatever, and somehow they should worry about newtons and this kind of crap. No, they should just understand that different substances are accelerated, and if you can accelerate their littlest tiniest bits, that if you can hit them with a whole bunch of slow moving bullets, it's a lot easier to get them moving than if you hit them with one big bullet.
Abbreviated as capital N. Discover something big in physics and you might get a unit named after you. So let's play with our new tool.
I hope they just name them after my favorite things. The fucktard, the asshole, the fucking girly physics. Yeah.
F equals ma. Let's push our square cow around. Maybe it has a mass of 5 kilograms. It's a baby cow. We push this baby cow with a force of 10 newtons. what will its acceleration be? We'll write down F equals ma, solve for a equals...
Yes, only in a perfect world. So it really has nothing to do with reality. This is just absolutely useless in the real world, because the real world means, how am I pushing the cow? What am I using to push the cow? Is the cow in a box, and the box is in space? Is there some way I can apply the force and have some efficient way to get the force through the object? Or am I just going to break its legs? Again, if you stand up in a spaceship and I shoot the spaceship too fast, that is, I force it to launch at too many G's, it's just going to break your legs. It's not going to move you faster. It's just going to break you into a pile of jello.
Equals F over M. My F was 10, my M was 5, so that equals 10 newtons over 5 kilograms.
So if you turn the force into gravity, so that would be the way to look at it. If you turn the application of force and always just make a conversion and say, I'm going to turn the amount of force my hand is applying, and we're going to pretend it's going to hit the object as gravity, then this equation can work. Because then you're applying the force as efficiently as the force can be applied. It can't be applied any more efficiently than in the form of momentum bits. Okay, the same bits that make magnetism and light, those are the bits. You have to convert it into bits that will affect nuclear pieces.
So my acceleration equals 2 meters per second squared. Ta-da! Double the force and you double the acceleration. If you represent this graphically, you get a really cool way to visualize Newton's second law. So I'm graphing F versus A, and I get this line. What's the slope of this line? The slope of this graph is an object's mass. That's really cool. Fantastic. Now we got the first...
Right. So the force, you always absorb as much force as you have mass. So again, yes, you'll absorb more force if you have more atoms. If you have more atoms in the same amount of space, you'll absorb more force. More raindrops will hit the atoms, and therefore you will be moved more. More energy will be used. But you'll move just as fast as if you had less atoms, because all you're doing is moving electrons and protons. You're never moving objects. You're just moving electrons and protons.
Two of Newton's laws. Newton's first law.
See, that would be the way to say it in modern days. A modern physicist should just make it clear. All you're moving, when anything's moving, is electrons and protons, and you just have to calculate how much energy it takes to move that many electrons and protons. Period. Done.
Inertia exists. His second law gives us a way to measure it. What can we do with them? I want to pause for a second and go off on a little bit of a tangent related to gravity. But it's
Yes, well, you're not the tangent. Well, my tangents are much better. My tangent is, there's no point in talking about acceleration as if it's a constant thing, because it's not. It really does depend on how you're applying it. There's an efficiency to how things accelerate in the real world, and so this equation is of no value when you're talking about different things you're attempting to accelerate, and all the losses that you can have in terms of deformation.
an exciting tangent. We never talked about why the force of gravity, G equals mg. We never talked about why the force of gravity is m times g, even though we've already used...
Yes, so g is just a constant for how much energy it takes to move an electron, for example, or a piece of mass. You could just calculate everything else in that number. So you could say the electron is 6.78, and then you could just say, well, how many 6.78s, how many electrons make the same mass as a proton? And then you could say, well, it's 4,682. And so you just come up with relative numbers to one thing, and it's all about just moving electrons in the end.
It a bunch. But now, with F equals ma, we can think about why. In the case of gravity, a is g. That's the 9.81 meters per second squared. The gravitational acceleration due to the size and the density of Earth. And the crazy thing is that any object I drop near Earth's surface will fall with the exact same acceleration.
That's right, but the only thing being accelerated are the atoms. So it's the same speed because all the atoms are affected the same way. Every electron is the same, and all the protons are the same. So depending on how many electrons and protons you have, that'll decide how fast you'll all go the same speed, because all the electrons and protons are going the same speed. So the truth is, the Earth, I can just put a single atom in orbit, move it at the same speed as the Earth, and it'll travel the same exact path. And the truth is, that's a truth. I can do that. that will happen. Now, I can't put an electron and proton in because, as I pointed out, they do get dragged to death. They can't keep going.
If we ignore air resistance. You might have seen that viral video where a bowling ball and a feather fell at exactly the same rate inside of a vacuum. This is why. It's so counterintuitive.
Oh, she didn't want to pay for that. Yeah, I guess they cost money, so she didn't want to pay for it.
Intuitive though. Heavier objects should fall faster, right? So my force of gravity, if I replace G for A, is...
No, heavier objects shouldn't fall faster if you understand that it's just about the little tiny bits inside, and they're the only parts moving, and they're all the same size.
M times G. And yes, if you double the mass, then you do double the force, but two doublings end up canceling, and you end up with the same acceleration. Now we can think about a problem with gravity. For example, what force does gravity exert on a tiny cow with mass 1 kilogram? Well, F equals ma. F equals 1 kilogram times 9.81, about 10 meters per second squared. And the force of Earth's gravity on our cow is about 10 newtons. Ta-da! Gravity isn't the only force, though. Let's hoist our cow up into the air with a rope and look at the forces on it.
So again, you're just saying it's 10 newtons were used up. 10 newtons worth of raindrops hit electrons and protons, and that's how many were used up moving the cow. That whatever she said, the 5-ounce cow or whatever it was.
We're going to do it safely and humanely, of course. Why? Because our cow is afraid of stairs. So now the cow is hanging there from a rope attached to the roof. My cow's not moving, even though we know that there's a downward force acting on it from gravity. Its acceleration is 0. But wait, what?
So again, its acceleration isn't 0. Its acceleration is still 10 meters per second in one direction, and it's feeling the tug right up here where you tied it to its nuts. Let's say the string was tied to the cow's nuts. He's feeling it, no doubt about it. He's feeling the pain. Okay, he's feeling that 10 meters per second tug on his poor little nuts. Okay, so there's a counter force pulling, and you know the two could be ripped right off. You know, and that's the fact. So there's not no force. There's two opposing forces now in effect, and the other opposing force is actually connected to the ground. So the ground is pushing the cow back up. You've just inverted the place from where you're pushing. Ugh.
F equals ma. Gravity didn't just turn off, so F isn't 0, and the mass didn't change. So how can A be 0? Well, if there's a downward force of 10 newtons...
See, it'd be so simple for her just to draw this imaginary floating cloud roof thing, whatever this is, and just put a little steel thing down here to the ground, just demonstrating I'm just inverting the ground. I'm putting the ground on the other side of the cow, and I'm going to do exactly the same thing the ground is going to do, which is push it up. But no.
Which we just calculated, then there must be an upward force of 10 newtons balancing it out. Where did that force come from? Well, it comes from the rope pulling up on the cow's weight. The force is called tension.
You're right, and it has nothing to do with the rope, because no matter what you connected it to the ground with, a steel rod, it wouldn't matter how you connected it, it would be exactly the same force, because it's really the earth pushing up. Period. Okay, so that's all you can do. If you tied it to a cloud, you'd end up pushing the cloud down, you know. But anyway, it doesn't matter. That's where the force is coming from. The ground is pushing back up.
Now we have a new force. My upward tension force and my downward gravitational force balance out for a net force of 0. And F equals ma makes...
So again, there's no net force equals 0 in the sense that obviously all the forces are still in play. So the object is in fact doing both things. It is in fact moving up, and it is in fact moving down. The atoms are doing that. The electrons and the protons are constantly in either going up or going down. They're not just sitting in one place going, everything's just fine. They're not doing that. They're in a field of momentum. There's momentum moving in both directions, and they are in fact being pushed both ways. And just as much as them goes one way as goes the other way. So like a school of fish that doesn't go anywhere, and some of the fish are going that way and some of the fish are going that way, the fish are still really active. Well, the thing suspended there is still really active. You just don't see it because it's happening. The activity is on the molecular level. It's on the level of the electrons and protons, which are doing plenty of moving. and now creating their own gravity by doing so.
Total sense again. No force, no acceleration. And we have a new concept to think about. When you have an acceleration of 0, your net force...
Well, acceleration just means change. So all acceleration means you're going to change how something's moving. The assumption is anything can be moving, anything, we don't know what's standing still in the universe. We can't tell. Everything moves collectively, and as groups we move. So I'm moving through space at the same speed as all the rest of the crap in this room. And again, it's only change. So acceleration just means I'm going to change the forces that are acting on you. They don't undo anything. It doesn't mean there's no forces acting on you already.
Must be 0. And it's important to remember, it's not always a single force acting on an object. There can be multiple forces, and they can be fighting each other, canceling out. They might be working together, adding up. But the fun of F equals ma is thinking carefully through all of the forces to figure out their net effect. For example, there's this weird substance called ferrofluid, which is essentially tiny iron particles suspended in oil that altogether make up a magnetic liquid that looks like it came straight off an alien spaceship. It looks so weird. And if you wanted to predict how it behaves, you would have to add up...
Why doesn't she point out how, well, yes, and people are using it to deceive other people into thinking light can be bent by magnetism when it can't, It's a gimmick. It's a little, it's more sideshow fun. Just create a freak show with your little fake ferrofluid images and pretend you're doing UFO science.
The forces on it from gravity, any magnets nearby, from the fluid forces between the trillions of molecules, and it gets quite complicated. We will stick with smaller systems. So let's play some more.
So I don't know. So she has a hint of, well, look, I could illustrate lots of things. I could show you gravity's effect on that fluid, and show you how it's sloping the straight line force of the magnetism. The straight line force of the magnetism is saying, create nice straight lines, but then the external force is forcing those lines to be curved because it's creating another force coming in another direction, changing the its
super common
appearance.
Problem from physics to see how you sum up forces. Let's keep the same 1 kilogram cow hanging from a rope and now hang another cow underneath it. Second cow is slightly heavier, 2 kilograms. So now let's think through the forces. F equals ma. The force from gravity on my second cow, m is 2 kilograms, times a is about 10.
Again, it's all going to add up to the same thing, so we won't bother. We've done enough of this, I think. So anyway, they don't know what they're talking about. They're talking like they've answered these questions. They know what a force is. They know what the laws are. They know what blah, blah, blah. And they really don't. They really don't understand any of it, and they don't even understand what Newton was describing, which is, again, it's all related sort of to the idea of the gravity force. He's using that as the icon or the thing to represent it as. That's the perfect force applied in the perfect way, where everything else is something less than that. It can be made out of it, the same stuff, but it's the same stuff in a completely different form, which means it's not going to have the same effect. Difference between a light bulb and a laser beam. But anyway, I've done my job here. This is just garbage, junk science, terrible physics, not even trying to do it on purpose, not even trying to be, let's say what we know, not what we don't. Let's not assert things that are beyond what we have proven or demonstrated completely. And again, there's just these glaring things that sit out there. I'm sure in this video she's not going to mention, wave interference and all that kind of crap. But I mean, this is all just garbage. It's junk science. They never thought through any of this stuff thoroughly, and they just jumped the evidence. It's that simple. Newton wouldn't do it. Newton kept getting harassed. Tell me why. Tell me. How does it do it? And he says, this is what it does. I don't know how it does it. And these people won't do that. They won't show that integrity. So anyway, until the next time and such. Do hate this planet. Alright, let's see if this actually saves.